Okay, so where do we leave off last time? We were talking about geometries. We held up some models and we looked at the basic geometries. We even replaced some of the bonds to atoms. We replaced them with lone pairs and thought about those geometries. So we got it in our head that there are basic parent electron geometries, linear, trigonal planar, and tetrahedral. And then we considered molecular geometries, with the geometries of only the atoms, even if there are lone pairs. And we decided there are a few of those that are a little bit, they're different. They can be different than their parent geometries if there's lone pairs. And so some of the words that we used to describe some of the geometries that we saw were bent, trigonal pyramidal, and really those are the only two words that are new, right? In this course, you don't have to worry about things that have more than 4 bonds because it's introductory chemistry. And so there's really not a whole lot of structures to learn when it comes to the different possibilities. Now, if you have 5 or 6 bonds, all of a sudden things get to be a little bit more complicated and you really have to think about it a little bit more. But that's not the case here, so you don't have to worry about it. The reason that I introduced the geometry part first is because you need to be able to have some level of visualization of the structures in your mind in order to think about how to draw or what's going on when we draw these Lewis structures. So that's what we're going to move into. We're going to move into drawing Lewis structures, which are essentially pictures of molecules. The problem is that the pictures of molecules don't have anything to do necessarily with their geometry. They're not exact replicas or exact drawings of real molecules. And there's often a disconnect. And so that's why I wanted to do the geometry part first, because I didn't want there to develop a disconnect and then add the geometry later and then kind of like not have this based in actual 3-dimensional space. But drawing molecules is really just an algorithm. It's just a set of rules, and as long as you process the rules correctly, then you get the picture right. But if you mess up on the rules, then you don't get the picture right. And we use electrons to do it. So let's dive in. I think I'm done explaining, and now we need to do. So I'm going to go ahead and get the whiteboard up, and we're going to move forward with that. I always show you my last bits of organic chemistry to get you excited about taking organic. Does it work? Totally. Everyone knows you're a nerd, Diana. Okay. Let's start off with something. How many valence electrons does carbon have? Do you remember how to look at the periodic table and decide that? Yeah. It's based on the row, right? Or the group, excuse me, not the row, the group. It's based on the group. Group 14, that's where carbon is. And so it has 4 valence electrons. So I implied earlier that Lewis structures don't directly relate to 3-dimensional geometry, that you can figure out the 3-dimensional geometry if your Lewis structure picture is right. So there's a limitation. There's a limitation in Lewis structures. Well, Lewis structures actually come before that. There's Lewis dot structures, and you can still sort of think about how things get bonded with Lewis dot structures, but there's even more limitations with that. So I'd say that there's a good number of chemistry faculty that spend a lot of time on Lewis dot structures, and I just don't, because they're even at our level of chemistry, they're just too limited to successfully predict the bonding in a lot of different molecules. And so I just don't spend my time with them. I move on to the slightly less limited Lewis line structure. But I do need to mention a Lewis dot structure. And a Lewis dot structure is a picture of valence electrons. And the only rule is that you draw little dots around the symbol of the atom to represent the valence electrons. And the only rule is you don't pair them up until you get more than 4. So if you take a look at something like oxygen, what does oxygen have? 6 valence electrons? So for oxygen, we would go 1, 2, 3, 4, 5, 6, and you just make it you just try to make it symmetrical, the picture. That's really the only rule that I have. I think nitrogen has what, 5 valence electrons, so you would do something like this: 1, 2, 3, 4, and then which one do you pair up? That doesn't matter, whatever. Pick one. Pick one. What about hydrogen? Hydrogen has 1 valence electron, so it would be something like this. So let me show you how this could work, right? Let's do something like CH4. Well, the idea is that molecules want to bind together so that they have 8 electrons in their valence shell, or at least at the very least, their electrons they're paired up. And so you can see, if we took CH and Lewis dot structures of hydrogen, that we could pair these up and we could say, okay, this is how it bonds. It's H, carbon, H, H, H. If you took a look at N2 though, how do I bond N2 together? I mean, it doesn't seem obvious to me how to get these two things together so that all of their electrons are shared. I can do something like this, but I still have to deal with these. How do I deal with them? Maybe I can just say, okay, these get bound together and these get bound together. That's certainly, you could say that, and you'll see that that's not a bad idea. But at the end of the day, Lewis dot structures aren't obvious when it comes to making molecules. Now, we're going to use the idea that atoms want to have 8 electrons, and I'm personifying them. They don't really want anything. They don't have emotions, but that what we're really saying is their most stable configuration is when they have 8 electrons. And I think you know this from the ideas behind ions. What about oxide? What about neon? And what about sodium ion? How many electrons do they have? Valence electrons. Well, let's look at neon first. Neon is in what group? It's group 18. So neon has 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay. What about oxygen? How many valence electrons does it have? This is where the valence electron counting becomes a little bit more of a challenge, and you got to go back and remember what it means to be an ion. You gained or lost electrons. Oxygen gained electrons because it's negative, and it gained 2 because it's a -2 charge. So if oxygen, when it's neutral, oxygen atom when it's neutral has 6, then when it's charged and it's -2, it has 8. And this is what I'm going back to. It's not inappropriate to say that atoms want to have 8 electrons to be stable. They just don't, they're not, now this isn't an atom anymore. It's an ion. Now there is another rule with dot structures. With dot structures, you have to, if it's an ion, you have to put a bracket around it. And in this bracket has to include the charge. I don't actually know. Why can't I go back and redo it? Folks at Procreate need to get better at their jobs. Okay. So this is for ions. You need to do this for ions. And so this is unless you'll, well, no, you'll see. It's still safe to just do it. Yeah. Well, really, you don't have to do it for cations. And I'm going to show you why in a second, Adi, but it's not wrong if you do it for cations. Let's take a look at sodium ion. Well, sodium, when it's neutral, it has 1 electron. If you take a look, it's in group 1, so it should have 1 valence electron. When it becomes an ion, it loses 1 of those electrons and it becomes charged. So we can represent it like this. Now, what happens to it? When it becomes charged, it loses 1 electron. So sodium is isoelectronic with neon. So it now has 8 electrons in its valence shell. We don't write the electrons. We don't show them. That's just convention. But that's why it takes a +1 charge, because losing 1 electron gets you to that 8 electron valence shell. So what if I wanted to talk about the Lewis dot structure of an ionic compound? Well, I would write down some brackets that indicate their charges. It doesn't really matter. I'm just circling. The circles don't mean anything. So if you take a look at right here, I don't use circles there. What I was using the circles for was to point out that it's sort of, these are, oh, well, we could pair these together. We could pair these together. We could pair these together. We could pair those and those. Same thing here is I'm like, okay, well, I can pair those together. Maybe I can consider these are paired together too. It's just to indicate it. Let's do one more example. What about potassium oxide? Well, that's got 2 potassium ions. So how would I draw the picture for this one? Well, I'd put a the charge goes on the outside of the bracket. Oh, so I need to draw the other potassium. This is how you do it for ionic compounds, because remember, ionic compounds don't actually share electrons. They're just charges that stick together. So that's a Lewis dot structure, and they're pretty limited, I think. So let's move on actually and talk about Lewis structures. Okay. So it uses valence electrons to draw line pictures of molecules to represent bonding. So what I'm going to do right now is I'm just going to draw a few pictures. I'm not going to show you the rules yet. I'm going to give you an idea of what they look like. So instead of having the dots for CH4, we'll use lines. This might be a little bit more along the lines of what you think about when you see a picture of a molecule. Okay, so here's some Lewis structures. So what I need you to be able to do is I need to teach you how to draw these and how to do them with the system so that your pictures are right. Right? If I just told you, what's the Lewis structure of CH2O, would you have automatically come up with this? I'm not sure. So let's work on that. I'm going to shrink this down to nothing because what I want to do now is I want to try to keep a running tally of rules. And this is how we do it. The first thing we do is we count all valence electrons. So let's give an example. Let's start off with the good old simple example, CH4. How do we count the valence electrons? Well, we look at each atom that's in the formula. We've got a carbon and we've got 4 hydrogens. We've already established that carbon has 4 valence electrons, and there's one of those atoms. So there's 4 valence electrons brought into the, I call it the game, whatever, the Lewis structure picture, from carbon. From hydrogen, it has 1 valence electron. There's 4 of them. So from all 4 hydrogens, I've got 4 more valence electrons. So my total is 8. 4 plus 4 is 8. Okay. Everybody okay with the first step? Great. Step 2. Step 2 is to arrange atom symbols. And how do we arrange them? This is the important part. symmetrically. Use the first atom as the central atom unless it's hydrogen. Okay. So we're going to arrange them symmetrically. We're going to use the first atom as the central atom unless it's hydrogen. And so why am I not adding any other information? Because at the end of the day, they all have to be bound to each other. And so drawing pictures like this don't actually represent molecules. So if you want to draw an accurate picture of a molecule, molecules will bind in very simple, straightforward patterns. So I think the words arrange the atoms symmetric, the atom symbols symmetrically, and use the first atom as an atom that goes in the middle, that implies that there's generally an atom that's central and everything else connects to it. So that means this is okay. The first picture I showed you isn't okay. This isn't okay. It's not okay if I do hydrogen and then have a carbon here and a, let's see, another hydrogen here, a hydrogen here, and a hydrogen there. That's making hydrogen kind of in the middle. All of these things are not symmetrical. Now, let me ask you a question. Is this symmetrical? Is this right or wrong? You're drawing pictures, ladies and gentlemen. So as long as you're following the rules, then you're okay. They're both technically right. Now, by convention, just by habit, you will see this way. This is how you'll see it. We're getting to that point, Adi. Just wait a sec. That is actually the very next step. Okay. Now, remember, this is the important part. You're not just drawing lines. You're not. Every stroke of the pen has some relationship with reality. And in this case, we're using valence electrons to draw these pictures. So we are going to draw lines next to represent the bonding in the molecule. But we're doing so in a way that is consistent with reality. We're going to use the valence electrons to do that. We're going to draw a single bond We're going to draw a single bond from each atom to the central atom. But then we're also going to reduce the valence electron count by the number of valence electrons used. So this is what I mean. Line, 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 line. But each line represents a bond, and each bond contains electrons. How many electrons are in a bond? Do you remember this from 6th grade? Anybody? Each bond represents 2 electrons. Each bond represents 2 electrons. So I drew 4 bonds. 4 times 2 is 8. So when I reduce the valence electron count, I reduce it by 8 that I drew in bonds. And so now I have 0 electrons left. So what I tell my students at this point is, look, all of the electrons that you can use to draw this picture are already on the page. Okay. Next step, check for octets. Okay, and I'm gonna, off to the side, I'm gonna put down the octet rule. The octet rule is the idea that atoms I'm gonna write it in a way that doesn't personify the atom. Let me say this. The lowest energy, and that means favorable configuration for atoms is to have 8 valence electrons. Big asterisk. Okay, so we want to check for octets because the idea is that every atom really is trying to get to this lowest energy state. That means it's favorable. And in order to be in this lowest energy state, you have to have 8 electrons. This is the octet rule. And the reason I put a big asterisk on there is that it's not really a rule in the sense that it's hard and fast and it's unbreakable. What is an octet for one atom isn't necessarily an octet for another atom. Generally, octet means 8. But we're going to see in a second that hydrogen doesn't want 8 electrons. It's only got 1 proton. It's only got 1 proton. So having 8 electrons would mean that it had a charge of -7. That's not. We've seen -1, we've seen -2, we've even seen -3. We hadn't seen no -7. I love to be dramatic. We haven't seen any -7. My mom is an English teacher. She would correct me. So it's called the octet rule, but we're going to find out real fast that there's lots and lots and lots of atoms that can break the rule. In fact, in general chemistry, we're going to say, look, there's actually only like 4 or 5 atoms that always follow the rule. All of the rest of the atoms on the periodic table regularly break the rule. And so I don't know why we call it the octet rule, since it's really the octet exception. But I mean, in introductory chemistry, rule isn't too bad because you don't see the exceptions too often. But there is an exception here with hydrogen. So generally atoms want 8 electrons, but one of the exceptions is hydrogen. It only wants 2 electrons. So let's check for octets. Let's check now. How many electrons does carbon have around it? I'm going to count both of these. So that's 1, 2, 3, 4, 5, 6, 7, 8. I'm going to count them both. I'm going to count both electrons in the bond. So carbon has around it 8 electrons. This is the idea about sharing, right? Why the heck would carbon want to share electrons with hydrogen anyway? Because if they shared them, then they would get this octet. All right, so what about hydrogen? Does it have a, quote, octet? But remember, for hydrogen, it just means 2 electrons. Okay, so for this hydrogen, how many electrons does it have? 1, 2. For this one, 1, 2. For this one, 1, 2. For this one, 1, 2. Okay? So everybody has an octet in this case. Let me go back to my original picture. Here's the first important statement. If you use all valence electrons and all atoms have octets, you're done. You're done. You finished drawing the picture. That's how you know you're done. You know you're done, and you've drawn the correct picture when all atoms have octets and you've run out of electrons. That's how you know. Does all atoms have an octet? Yes. Did we run out of valence electrons? Yes. So we're done. This is the picture of CH4. Okay, let's try something different. So do we know what the octet rule is now? Does anybody have any questions about the octet rule? Because I'm going to erase this part. In fact, I'm going to go ahead and erase that. Hydrogen is one of the exceptions, but there are other exceptions. And the exception that you need to be familiar with is boron and aluminum. Aluminum's kind of a weird metalloid, so is boron. But boron and aluminum only want 3 sets of electrons, so 6 total valence electrons in order to have an octet. So let's do an example of what I mean by that. BH3. Let's do this one. Count the valence electrons. So what does boron have? Boron has 3. And there's 1 of them, so that's 3. Hydrogen has 1, and there's 3 of them, so that's 3. I have a total of 6 electrons to make the picture. So let's do the next rule. Arrange them symmetrically. Okay, did that. Let's draw, I use boron as the central atom. It's the first one listed. Let's draw a single bond to each of the atoms, reduce the valence electron count. 6 electrons are in the 3 bonds. Now I'm going to check for octets. Only exceptions here. Does hydrogen have an octet? Yes, because they have 2 electrons around each hydrogen. 2 of them in each bond. Does boron have an octet? 1, 2, 3, 4, 5, 6, we say yes. Boron has an octet because boron only wants to have 6 electrons once. And so we're done. We've used all the electrons and everyone has an octet, so we're done with the picture. So the exceptions that you have to know in this class are hydrogen, boron, and aluminum. And I think that's it for this course. That's it for this course. Yep. Okay, so do you draw them differently when it comes to the lines? What does that mean? No, one line. One line means 2 electrons. There was nothing different about the lines. Let me redraw the pictures. CH4 looked like this. BH3 looked like this. There's no difference in there. The lines represent electrons. If there's 3 lines, it means 6 electrons. If there's 4 lines, it means 8 electrons. The only difference about the number of lines is the number of valence electrons that it represents. Right? Right. It really is for hydrogen. If you would go back to the original electron configuration, to get a full shell, you only need 1 extra electron to get a full valence shell for hydrogen. For oxygen, your valence shell is the highest energy valence shell is the p set of orbitals. So remember, it can have up to 6. So in order to get it full, you need to add 2. 1, 2, 3, 4, 5, 6, 7, 8. And there's your 8 valence electrons, or -2. That's how that ties in together. All right. Again, though, for this, the only difference in the way that I've drawn this is because of how many electrons I need for an octet. Boron is an exception, so it only needs 6 electrons. Carbon needs all 8 electrons. So that means that the carbon needs to have 4. It doesn't, you're talking about because I drew the line like this or the line like that? Yeah, so remember what I said before? Is this any different than this when it comes to symmetry? Right? These are just as symmetrical. And so I said that by convention, we'll see it like this, but this is fine too. So that means that if I were to draw the lines, these would have to be at a diagonal and these would be up and down. But they're the same, right? That's the only information you can get, you can take from the lines is how many electrons there are. The angle of the lines makes no difference. If we're on the same page on that. Okay, cool. Good. Okay. So let's do another example. NH3. Let's try to run through the Let's try to run through the rules real quick. Count valence electrons. This is the last time I'm going to do this particular. This is the last time I'm going to draw it out like this. I'm just going to start to write the numbers down. But nitrogen has 5. There's 1 nitrogen, so that's a total of 5. Hydrogen has 1. There are 3 hydrogens, so that's a total of 3. 5 plus 3 is 8. So I have 8 valence electrons to draw the picture. So let me arrange the atomic symbols symmetrically. There's only 3 hydrogens, so in order to be symmetrical, I want to do it like this. But now remember that the picture that I draw isn't related to the geometry directly. It's only indirectly related, and I have to figure out the geometry based on my picture. And so we'll get to that geometry bit here in a second. Okay, so let's draw all those lines. 1, 2, 3. Reduce the count. I've used 6, so I have 2 left. So what do I do now? Do I have octets around everything? No. I use extra electrons to make octets with lone pairs. So this is how you end up knowing that an atom has a lone pair. It's because you've processed these rules in order. And you got to this point and you said, okay, I have 2 electrons left over. Hydrogen has octets, but nitrogen doesn't. Nitrogen only has 6. It's not one of the electrons, it's not one of the exceptions. So it needs more electrons. How many more does it need to have an octet? It needs 2. Now it doesn't matter where I show those 2. I usually pick the spot because I'm not a very good artist. There's always one space that's a little bit more open than the other space. That's a little bit more crowded, but it's not wrong. Electrons in this course will always 100% of the time go in pairs. In this course, electrons will always 100% of the time go in pairs. This full count will always be an even number. Okay. Now I recheck for octets. The reason this didn't get a number is because it's a static rule. If I use all my valence electrons and all atoms have an octet, then I'm done. So now everything has an octet. Lines count as electrons. Lines count as electrons, and so they count towards the octet. So let's count for nitrogen right now. There's 1, 2 in that bond, 3, 4, because there's 2 more in that bond, 5, 6, 7, 8. So you count the electrons in the lone pair, 1, 2, and then the bonds, 3, 4, 5, 6, 7, 8. So we're done. If you use all the valence electrons and all atoms have octets, you're done. Okay. Okay. Let's do another one. Water. How many valence electrons does water have? Hydrogen has 2, oxygen has 6, so that's 8 total. And when I say hydrogen has 2, I'm saying it has 1 each. There's 2 hydrogens. That's a total of 2. So I've got 8 valence electrons to work out. Let's arrange them symmetrically. I'm usually going to use the first atom as the central atom unless it's hydrogen. Since hydrogen is the first atom listed in this formula, I won't use it as the central atom. I'll use oxygen as the central atom in this case. Okay, let me draw my bonds. 1, 2. How many did I use there? I used 4. So I have 2 electrons left. Let me just make some room. Okay, check for octets. Hydrogen's fine. It's got its 2 electrons. It's oxygen that has a problem. It needs more. I did my math wrong. You guys didn't catch me. I have 4 left over. 8 minus 4 is 4. Yeah, and so oxygen needs 4 more electrons. So how do I do that? I do that in lone pairs. 1, 2, 3, 4. I've used all the valence electrons. I'm down to 0. So everything has an octet. I've used all the valence electrons. I'm done. Okay. Water has 2 lone pairs around the oxygen. What does it look like the geometry of water is based on the picture I drew? If you just look at this picture, you might say tetrahedral, or you might say it's linear. But some of you guys are already starting to remember the last time we got together, and that lone pairs influence the geometry. And so the parent geometry will end up being tetrahedral, and it will end up being a bent molecular geometry. And we'll talk more about that in a second. Okay, let's do another example. Let's do CO2. Okay, counting the valence electrons. I get 6 from oxygen, so 6 plus 6 is 12. I get 4 from carbon, so that's only 1, so that's 4, and then 4 plus 12 is 16. I get 16 valence electrons total. Yes, hydrogen will always be around some atom. You could draw the Lewis structure for H2, though. That's what you'd end up with. Okay, so let's arrange the atoms. Carbon is not hydrogen, so it's going to be the central atom. In fact, carbon is always the central atom in this course, if there's a carbon listed. Okay, now this is a very important point. CO2 is going to end up with double bonds. And so this is the point in the rule set that I'm going to talk about multiple bonds and how you know when to make multiple bonds. Students often get confused and make mistakes with multiple bonds because they do not process these rules in order. They just start throwing multiple bonds out there, and then they're going to get things wrong. You only use multiple bonds when you have to. Let's find out when you have to. Let's start off with my lines. Let's reduce my count. I'm down to 12. Okay, so I've done 1, 2, and 3. Let's check for octets. Nobody's got an octet. Nobody. So let's go ahead and let's use extra electrons to make octets. 1, 2, 3, 4. Carbon is done. 5, 6, 7, 8, 9, 10, 11, 12. That's all I had. I only had 12. I don't get to make more electrons. I only have so many valence electrons. What did I do? Did you run out of valence electrons? Before making octets? You erase them and use them for double or triple bonds. Are there two P's in triple? Yeah, I didn't think so. Okay, so remember that in the picture that I'm working on, I've already used all of the valence electrons that I have to make the picture. I don't have any more. So I have to use the electrons that are there to get octets for everyone. Because remember, the rule is if I have used all of the valence electrons and everything has an octet, then I'm done. All right, so let's erase them and make double bonds. Well, when I erase them, I have to erase them in pairs, though, right? Because everything happens in pairs. A bond has a pair. Let's do this. What happened? Let's examine. Let's examine only the oxygen. Yes, I've got some electrons around the carbon and the other oxygen. Let's ignore those for now. How many valence electrons are around this oxygen? I have 1, 2, 3, 4. How many are around the carbon? I had 1, 2, 3, 4, 5, 6, 7, 8. I had 8. Let's examine it. What happened when I drew the picture like this? How many now? What does the carbon have? 1, 2, 3, 4, 5, 6, 7, 8. The carbon still has 8 around it. What happened to the oxygen though? 1, 2, 3, 4. It went up to 6. It went up to 6. Okay. This is why we make double bonds and triple bonds. Because if you move a lone pair from one atom and use it to make a multiple bond between that atom and another atom, it doesn't change the count around that atom. It just changes the count around the other atom. Okay, let me erase this because this is where things get complicated. This is where things get complicated. And so let me put it in a big red warning. This part is anything but straightforward, and you're going to see. We never have more than 8 valence electrons. And that's in this course. In general chemistry, we'll talk about the exceptions to that rule, but not in this course. So in this course, you never have more than 8 valence electrons, never. And so this is going to guide us in how we erase them and use them for double or triple bonds. This is how we do that. What still has an octet that and what what still needs to get an octet? Well, I've said that I have 8 here. I have 8 here. I only have 6 here. So I need to get electrons to move that way. And so how do I do that? Let's start erasing. Let's figure this out. Let's figure this out. Okay, let's think. Can I do this? Let me erase this. Does this work? Oh. This one actually does work, but there's a problem with it. Carbon has 8, oxygen has 8 on the right, and oxygen has 8 now on the left. But another important, and so this is where the limitation, it's not, that's right, exactly. This is an important part. I'm not, because there is another rule that you can do to check whether this is okay. Because just having an octet is not the end all be all to being okay. There are more things to check on. But in this course, we don't teach you those things to check on. So what we do is we sort of use a more general rule. We keep it symmetrical. We keep it symmetrical. Let's go back to the way that I had it before. It was this. Is there a way to arrange these more symmetrically? Is there a way to arrange these more symmetrically so that I have 8 around everything, but the picture is more symmetrical? So in this picture, I have 8 around everything, but it's not symmetrical. So let's try to do some of this work. What if I were to erase those, and I want to put them here. 2 of them were already there, and I erased them from the carbon and put them on the oxygen. So now what do I have on the oxygen? 1, 2, 3, 4, 5, 6, 7, 8. Now the carbon only has 6 because I moved 2 of them over. What about this one? This one has 8 still, but I can also erase 2 there and make a double bond here. And now I have 8. So which picture is more symmetrically oriented? Which one looks more symmetrical? This picture looks more symmetrical. This is the right picture. This is the wrong picture. It really is difficult in this last step in this class because you don't have the other tools that I would give to students in general chemistry, because I'm not going to complicate it to that level. And so it really does end up being about how you draw that first picture. Let me show you what I mean. This is how I drew the picture to begin with. I did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now I could have done it differently. I could have done it like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're in the same situation. I don't have an octet around the carbon. So I want to apply rule number 6, but it becomes a little bit more straightforward, right? If I apply rule number 6, I need to erase some. Ooh, that's a big eraser. I need to erase some and make a double bond. I need to erase some and make a double bond. I end up with the same picture, but what I'm trying to illustrate to you is that how you process rule number 5 will dictate how difficult rule number 6 is. And I don't have any advice. Maybe start on the outside. Maybe that's the best advice I can give you. But I'm not going to write it down as a rule because you just need some practice. Okay, so that's CO2. You're done with CO2. Let's keep going. I need to do another example. Let's do O2. And then let's do N2. So what's O2? It's 6 plus 6. That's 12. I have 2 oxygens. If I only have 2 oxygens, I just put them next to each other. Let's draw the single line there. Okay, did that. Let's remove the electrons. So I'm down to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't have an octet around the left oxygen. So let's erase. And use them as multiple bonds. Did the double bond work? Do I now have octets around everything? Yes. So I'm done. Okay. One more example. Let's do N2. Now you'll see how we get to N2. Well, we'll do 2 more. N2 and then we'll do CH2O. All right, so N2, my count, 5 plus 5 equals 10. So arrange the atoms. That's how you do a diatomic molecule. Draw my single bond, reduce the count. I have 8 left. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now I need to keep erasing. So let me erase those and try a double bond. Did that work? Well, it does increase the octet around the left nitrogen, but the left nitrogen now has 6 instead of 4. It still needs 8, so I got to keep going. I'm going to keep erasing and trying multiple bonds until I got my octets. Here we go. 1, 2, 3, 4, 5, 6, 7, 8 around both nitrogens. Now I'm done. So there's a triple bond in this case. C2H2. This one's a little bit more of a challenge. How do I arrange this one? I'm going to give you, this is how we do it. No, every atom has to have an octet. How many electrons do I have? 4 plus 4 is 8. Plus 2 is 10. Let's try. 1, 2, 3. So I used 6. So now I have 4 electrons left. So 1, 2, 3, 4. The carbon on the right still needs an octet. So let's try to make a double bond there. That's got 6, but it still doesn't have 8. So I'm going to keep erasing. Now everyone has an octet. Let's do the last example. The last example is C2 or CH2O. CH2O. Let's do the valence count. Oxygen has 6, carbon has 4, and I get 2 from the hydrogen, so that's 12. Let's arrange the atoms as symmetrically as possible. Now let's draw my one line. That was 6. 12 minus 6 is 6, so I need 1, 2, 3, 4, 5, 6. Does everything have an octet? Does everything have an octet? You should see that carbon does not have an octet yet. So I need to erase and try a double bond and see if that works. Now carbon has an octet, and so does oxygen, and so does hydrogen. So this is my picture for CH2O. Okay, and so that's the rules. That's the rules. So let's move on to the geometry bit. So now that you know how to draw Lewis structures, let's take a look at Lewis structures and let's see how do we use them to figure out geometry. And you already know, right? Because we already know that bonds and lone pairs are geometry groups. If you have 4 geometry groups, what's the parent electron geometry? What is 4 electron groups? What's the parent electron geometry? How do we figure out the geometry? 4 electron groups, and all of them are bonds. 4 electron groups, and all of them are bonds. Right? It's tetrahedral. What's the molecular geometry? What's the geometry of only the atoms? It's still tetrahedral. Okay, let's go back to another example that we did today. How do we do this geometry bit? I had N, H, 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 and it had a lone. Let me just draw that a little bit better so that it's not so sloppy. Had 1 lone pair. How many geometry groups are there? How many geometry groups are there? 1, 2, 3. Don't forget about the lone pair. 4 geometry groups. What's the electron geometry? Still tetrahedral. But what's the molecular geometry now that one of the geometry groups is a lone pair? Not planar. It's not planar. It's trigonal pyramidal. It's trigonal pyramidal. Right. Electron geometry is the same as the parent geometry. So 4 electron groups gives you a tetrahedral parent geometry or electron geometry. The molecular geometry with 1 lone pair is trigonal pyramidal in that case. Okay, let's keep going. Let's get another example that I had today. How do I sort out the geometry? Here's another example that I used. I said, what about water? How many geometry groups are in the water? 1, 2, 3, 4. So what's the electron geometry? It's tetrahedral. But what's the molecular geometry now? 2 of them are lone pairs, so only the atoms. What's the shape that only the atoms make? Bent. Bent. Okay, let's go back to another example. It involved 3 geometry groups. It was the last one that I did. It's still up there in the corner. It was CH2O. What's the geometry around that carbon? How many geometry groups are there? Here's an important piece that students need to figure out. Need to make sure you're on the same page with. A double bond or a triple bond only counts as 1 geometry group. Right. So this one only has 1, 2, 3. A double bond or a triple bond only counts as a single geometry group. So what's the electron geometry here? Trigonal planar. What's the molecular geometry? It's the same, right? Trigonal planar. Okay, I want to give you an example that's in the 3 electron geometry group region, but is not also, doesn't have the same molecular geometry. So in order to give you an example like that, we need a whole new molecule that we haven't done yet. So let's put it all together. Let's put all of these skills together. SO2, I want to know the geometry of SO2. All right, let's do it. Let's count the electrons. 6 from sulfur, 6 from each oxygen, so I have 18. Sulfur is the central atom, so let's arrange everything symmetrically. Why can't I get that oxygen as far away as the other one? There we go. Now let's draw a single bond to make octets. How many did I use? I used 4. So let's reduce our count. I should have 14 left. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. Sulfur still doesn't have an octet. Yikes. So what do? I erase. Oh, my eraser's so big right now. I erase one. And actually, just for symmetry's sake, I'm going to erase those just because the picture looks better. And now I'm going to make a double bond. So oxygen on the left has 8. Oxygen on the right has 8 by virtue of 4 in the double bond and 2 lone pairs. But now sulfur also has 8. 2 from the lone pairs and 6 from the bonds. And so this one isn't symmetrical because the bottom line is that the most important thing is that everything have an octet and that I use all the valence electrons. Now, in general chemistry, we're going to show you another reason why this particular picture isn't actually correct, but we're going to leave it like that in intro chem. So in intro chem, this is what we're going to do. We're leaving it like this, and because we don't take it to the next level. But this is fine for now. So let's count the geometry groups so we can figure out the geometry. It has 1 geometry group here. It has 1 geometry group there, and it has 1 geometry group there. So that's 3 geometry groups. So what's the parent geometry? What's the electron geometry? Trigonal planar. Okay, with one lone pair in the trigonal planar electron geometry, what's the molecular geometry? Yeah, it's bent. Okay, that's it. I mean, let's do one last example to make sure that we're all on the same page. We did oxygen or nitrogen earlier today. Let's just do Nitrogen, it had a triple bond. How many geometry groups are, ooh, hold on a second. Let's not use that one. Let's use CO2. This is the picture that we came up with CO2. That's a much better example. How many geometry groups here? How many geometry groups here? Yeah, 1, 2. So this is 2 geometry groups. What's the electron geometry here? Linear. Linear. Right? Linear. And the only possible geometry for nitrogen is what? It's only 2 atoms. Yeah, the only possible geometry between any 2 points is linear. Okay, so that's it. The only other thing that I got to show you when it comes to, and I think you already know this, is what about the bond angles? Well, I'm going to use generic atoms now. This is linear. What's the bond angle here? What's the bond angle? Yeah, this is a 180 degrees. We talked about this last time we were together. What happens if I have something that's trigonal planar? What are the bond angles here? Yeah, this one is 120 degrees. The only thing that I didn't talk about specifically is what happens in this situation. And I'm going to use the 3D model. This is the tetrahedral model. What's the bond angle in a tetrahedron? Does anybody remember what it is? Yeah, that's it. It's 109.5 degrees. So you do have to know these bond angles. And the bond angles are all associated with the 3 parent geometries. Okay. The bond angles are all associated with the 3 parent geometries. And so if I give you a structure and I ask you what the bond angles are, then you have to decide what the parent electron geometry is. But once you know what the parent electron geometry is, then you know what the bond angles are. So in this case, still up here in the corner, we decided that the parent electron geometry was what? What did we decide? For CH2O. What did we decide for that? Didn't we decide that it was 3 geometry groups so that it must be trigonal planar? Yeah, and so that means what are the bond angles? 120 degrees. Yeah. Okay, so there's one last piece. There's one last piece. And this is not something that we've talked about. But there's yet another thing that the iPad does that I have yet to figure out. Like, I don't know how to do that all the time. How cute is that? Must not be woke enough to figure out procreate. All right. Okay, electronegativity and polarity. Electronegativity is the tendency of an atom to attract electrons in bonds. And polarity means a separation in charge. And these things go hand in hand. If you have two atoms, X and Y, and they don't share electrons evenly, in other words, they're sharing electrons because they're covalently bound, but they're not doing it evenly because one atom has a stronger tendency to attract electrons. Then that means that the atom that is more electronegative will have the electrons a little bit more than the one that's less electronegative. And so that means there'll be a separation in charge. This is called a polarity. This is what we mean by polarity. Now, there is a periodic trend for electronegativity. It goes like this. You need to know this trend. And this arrow points at fluorine. Fluorine is the most electronegative atom. So if I have F2, here's the Lewis structure for F2. You would sort this out if you followed all the rules. Well, fluorine is very electronegative. Is this bond polar? Is there a separation in charge for this bond? Is the bond polar? Think about it this way. It's like tug of rope with two really giant teams, and the teams are exactly the same on either side. Yeah, there's a lot of pull on one side, but there's just as strong a pull on the other side. And so this one is non-polar. Is the molecule polar? Non-polar. Okay. What if I change one of these atoms, though? Is the bond polar now? Is the bond polar now? Yeah, it is polar now. Fluorine is more electronegative than hydrogen. Fluorine is more electronegative than hydrogen. Hydrogen is over on this side for this purpose. So I can draw a dipole arrow. This is a dipole arrow. This side is positive. This side is negative. So is the bond polar? No, the bond in this case is polar. The bond is polar. Yes. Is the molecule polar? Yes. There is a permanent separation in charges. Okay, let's do another example. I'm going to redraw that trend. I'm just going to make it a little bit smaller. Okay. What about this? Are the bonds polar? Why not? Yeah, it's because really that in this course, in very rare occasions, noble gases don't make bonds. So in this course, we're never going to show a noble gas making a bond. So we don't really consider electronegativity for noble gases for that reason in this course. Even when we do, fluorine's still going to be the most electronegative. But we're not going to do it in this course. Are the bonds polar here? Where's carbon? Carbon's over there. Where's hydrogen? Hydrogen's over here. What's more electronegative, carbon or hydrogen? Yeah, carbon. So are they polar? They're not the same. So are they polar? Is the bond polar? Yeah. What side has the positive end? Hydrogen or carbon? We're going to get to that in a second. Hydrogen is the positive end. So is the bond polar? Yes. Is the molecule polar? You ready, Angela? Is the molecule polar? No. The individual bonds are polar, but look at all of the dipole moment arrows, the dipole arrows. They all point in the same direction towards each other. Remember that this is a symmetrical structure. It's a tetrahedron. If I have bond dipole arrows, they don't actually sit on the outside of the bond. They actually sit directly on the inside of the bond. So they all point towards each other and they cancel each other out. The molecule is nonpolar. So what makes it nonpolar? There's no net dipole. All bond dipoles cancel. This is the reason that it's nonpolar, but I'm about to show you a quick way. You can tell that a molecule is nonpolar in this course if you just examine what's around the central atom. Everything around the central atom is exactly the same. Carbon bound to a hydrogen, to a hydrogen, to a hydrogen, to a hydrogen. 4 bonds to a hydrogen, nothing is different, nonpolar. So if everything is the same and nothing is different, the molecule is nonpolar. The only way that the bond is nonpolar is if it's the bond between 2 identical atoms. So let's do one last example of this polarity business and we'll be done. We'll be done. Let's do one last example. Let's see if we can put all this stuff together. Here was that picture for water. Are the bonds polar? Are the bonds polar? Yeah, right. Oxygen and hydrogen are not the same atom, so the bonds are polar. Is the molecule polar? Is the molecule polar? Is the molecule completely symmetrical? Is everything around the central atom exactly the same? Is the lone pairs the same as a bond to hydrogen? Are the lone pairs the same as a bond to hydrogen? No, they're not the same. They're not the same. So yes, the molecule is polar. If I draw it out in 3 dimensions, what do I have over here? I have a bunch of red negative space because of the lone pairs. I have a bunch of positive space because of the partially positive hydrogens, because they're less electronegative. So there is a net dipole moment. For water. Okay, so that's it. I'm going to stop it there. We're done.